You probably don't like the look of this. You have to differentiate it, and it doesn't really look like anything you've been dealing with.
Nope.
And you probably attempt to try and get that y on its own. Failing. Because this is not separable. How do you deal with a question that looks like this? And it's one of those moments where you've got to fall back to a great technique called implicit differentiation. And for this, we simply differentiate as we go along. But we've got to remember that y is a function of x. And therefore, we're going to treat it like that. So for the xy, we have to remember that it's a function of x, but deal with it specially and use the chain rule on the y squared. But we'll do it as the quick method where you can overall just use a few rules for implicit. And so it looks like this. With the xy, we're going to do product rule, because as you can see, we've got two functions multiplied together. So u is x and v is y. Nothing different than usual. Remembering that y is a function of x here, so we've got that assumption. U dashed is 1 and v dashed is 1 as well, but because it's a function of x, we've got that extra dy by dx. Now for product rule, as I use in my way without a formula, you're going to be multiplying opposites together. So we'll get x dy dx. We go from top left to bottom right, and then the other, we add 1y. So we just leave it like that. So that's the product rule for this section here. And we're going to now use just standard methods for there. So what we've got forming here is, yeah, I'll add it onto here. So 2y, so imagine it was a function of x. You would have 2y, but due to the chain rule, we've got dy dx like that. And generally, you know, if you're dealing with a y, you just treat it like it's x and then add dy dx. And then 8 will go to 0. Now, a lot of people at this point want to rearrange for dy by dx, and it's fine. At this point, you can treat it like a fraction and rearrange and find dy by dx, but you've got to look back at the question where it says at the point 2, 2. And one of the differences with many of the differentiation questions here is you're going to need your x and your y, okay? Because they have an x and a y in this expression. So there are two ways to go down, and I guess I'll do it for you because we're here and we may as well see it, and you can decide which way you prefer. So I'm going to call them algebraic and sub and rearrange. So for algebraic, we can essentially, let me use highlighter because it might be easier. We're going to look at the terms which don't have a dy by dx, and they're going to be slung over to the other side. And then the terms that do have a dy dx, we're going to factorize out the terms in front of them. So what do we have? What was I using? Black, I think. So what do we have left after that is an x plus 2y. I'll put it in brackets to make it nice and clean. And then we've shoved that negative y over the other side, or we've taken away y from both sides. And then simply dy of dx, write it properly, is negative y all over the x plus 2y. Now at this stage, obviously, we've got our coordinate, which is 2, 2. So dy dx is equal to negative 2 all over 2 plus 2 times 2, which as you can see is negative 2 over 6, which simplifies to negative 1/3. Obviously that's your answer, but you'll notice that if you're not a fan of algebra, you don't necessarily have to be rearranging it to find the answer, and you can reduce the amount of algebraic manipulation by substituting in straight away. So remembering that you have the point 2, 2, that will be 2 dy dx plus 2 plus 4 dy dx equals 0. And then obviously we can do the same sort of thing, but 2 dy dx plus 4 is 6 dy dx, and we move the negative 2 over, and then we divide by 6, and that simplifies to the same thing. Now I think the clear winner is the one where we substitute first, definitely for the follow-up. And it feels easier, but if you want to challenge yourself, you're going down the algebra road, keep challenging yourself. I hope that helps.